And now we're going to talk about the object-oriented and functional programming features in modern Fortran. For much of Fortran's history, people have been plotting the language's demise. On several occasions, the plotters have actually thrown down the gauntlet and made public calls for retiring the language. It turns out that the statements made in such proposals, however, make a really nice backdrop for describing modern Fortran. This 1991 technical report from Lawrence Livermore National Laboratory provides one good example. Let's look at the report's arguments. At the start, the report cites a debate from 1984 about whether to retire Fortran. The core argument hinges on the need for parallel execution. A major component of the proposed cure is a functional programming language, Sisal, that raises the programmer's level of abstraction above what was then feasible in high-performing Fortran programs. Now let's examine the motivation and aims of this alternative approach. First, by the time of the 1984 debate, it was already clear that future supercomputers would be multiprocessors. In fact, from the vantage point of today, we now know that even laptop computers have become multiprocessors since the dawn of the multi-core era in the early to mid-2000s. Achieving high performance on multiprocessors necessitates parallel programming. The report describes three desired characteristics of what it calls a true parallel programming language. 1. The language must insulate the programmer from the underlying machine. This is the piece about raising the level of abstraction. 2. Parallelism must be implicit in the semantics of the language. To put this in the words of Stanford computer architecture professor Kunle Olakotin, who is arguably the father of multi-core computing, Joe the programmer shouldn't have to deal with parallelism in any explicit way. 3. When the programmer desires determinacy, the language should guarantee it. Here the report's author is alluding to the fact that high-performing parallel programs do not guarantee determinism, because determinism requires synchronization, and synchronization hurts performance. For example, changing the order in which a series of floating point values are summed can change the resulting sum because of differing round-off errors. However, some purposes, such as debugging, necessitate determinism. Therefore, a complete parallel programming solution must provide synchronization mechanisms. Now let's look at the problems the report identified with what I'll call classical Fortran with respect to these two statements, A equals foo of x and B equals goo of y. Ideally, one would like to empower the compiler to determine whether it can parallelize across these two function calls. A problem arises when the compiler cannot determine whether x and y might be aliases for the same data. In classical Fortran, the primary aliasing mechanism was common blocks that enabled procedures to share access to data. Fortran 90 added another aliasing mechanism in the form of pointers. A now widely known solution to this problem comes in the form of functional languages. Such languages facilitate definition of functions that provide unique mappings from their inputs to their outputs. A given input will always produce the same output. This is accomplished by writing side effect-free procedures. Side effects constitute anything that affects the computer state in any way other than creating the function result, using the input data, and data structures that are local to the procedure itself. Examples of side effects include modifying procedure arguments, input and output, modifying data declared outside a procedure, and halting execution, although I find that labeling the latter case a side effect is somewhat akin to medical doctors referring to death as a complication. In the absence of side effects, programs are implicitly parallel. In the next video, we'll see how the arguments made in the process of calling for Fortran's demise actually turned out to be a prescient roadmap for Fortran's future. Each of the desirable features we just talked about now exist in the language. To illustrate, let's look at one of the most important partial differential equations of classical physics, the Navier-Stokes equations that describe fluid flow. What I'll show you in the next video is how modern Fortran's support for three major programming paradigms facilitates a translation of these equations into a high-performing parallel code leveraging the very concepts detailed in the Lawrence Livermore report. In particular, we'll see how the object-oriented programming features that entered the language in Fortran 2003 enable the definition of distributed objects on which the programmer can write a set of purely functional operators by leveraging the functional programming feature that entered the language in Fortran 95, that feature being the ability to indicate to the compiler that a procedure is pure, meaning side effect free. Ultimately, we'll also see how functional purity eases the construction of highly asynchronous, massively scalable parallel code using the parallel programming features that entered the language in Fortran 2008. As a very nice side benefit, we will also be writing clearer code by raising the level of our software abstractions to closely mirror the mathematical abstractions we would write on a blackboard. This follows advice nicely summed up by Professor Kevin Long of Texas Tech University, who made this comment to me when he was at Sandia National Laboratories in 2007. Kevin leads the development of the Sundance C++ finite element solver framework. When I first inquired about whether he encountered any difficulty in parallelizing abstractions similar to the functional ones I just showed you, he commented that they are actually easier to parallelize than more traditional scientific programs. I believe this is because they expose the parallelism that existed in the original functional mathematics before we translated that mathematics into an imperative programming language.